So today we are going to talk about thrust and the different components of thrust. Recall that thrust, which is a force, is mass flow rate times the exhaust velocity. And today we're going to talk about both of those terms individually. So let's start with the mass flow rate. What is the mass flow rate? Well, that is the rate at which we use mass. So mass is both the fuel mass and the oxidizer mass. When you combine the fuel and the oxidizer, the total mass that comes out is the mass of the fuel plus the mass of the oxidizer. If you want to double the thrust, you want your rocket to be like twice as powerful as it was before, there are two ways of doing it. You can either double the mass flow rate or double the exhaust velocity. Those things are not equal to each other though. One is much easier than the other. So let's talk about doubling the mass flow rate. You take twice as much fuel and twice as much oxidizer and expel that. You could do that simply by adding another engine. You have to obviously add all of the plumbing and everything that goes along with it, but if you added another engine and you plumb the whole system and you just use twice as much fuel, then you would double the thrust. If you double the mass flow rate, you use the fuel and the oxidizer at twice the rate, so you can only run your rocket for half as long. And interestingly, doubling the mass flow rate doesn't change the ultimate delta V. So it doesn't actually make your rocket go faster. You just get to that speed faster. So you double the acceleration, but you half the time that you can actually run the rocket. Let's talk about the exhaust velocity. So if you wanted to double the thrust, could you double the exhaust velocity? Well, that is much, much harder. So you have the rocket with the mass of the fuel and the mass of the oxidizer coming out. And the exhaust velocity is the speed at which that mass leaves the system. This is mainly controlled by chemistry and physics. So chemistry determines the energy that is released when you combine the fuel and the oxidizer. And the physics is like the nozzle design. So how you take that heat and turn that into momentum. So how can we double the exhaust velocity? Well, that's really hard to do because we're chemistry limited. So what that means is here's a chemical equation. And this chemical equation is you take some hydrogen, you take some oxygen, you combine them together and you get an extremely large explosion. It's like the Hindenburg, right? You take hydrogen, oxygen, you put them together, you get water as a result, which is really interesting. But then you also get heat. And the interesting thing, in my opinion, is that when you combine these two things, hydrogen and oxygen, you don't get just an unlimited amount of heat. You get an extremely precise amount of heat, 241.8 kilojoules of energy, an extremely precise amount of energy that you get out of this. No more, no less. And so what that means is that you can only extract a certain amount of energy from that reaction, which means that you can't get an unlimited amount of temperature or energy from combining hydrogen and oxygen together. And so what we need to do then is we need to figure out how to turn that temperature. We get a very precise amount of temperature out of this chemical equation. And then we basically turn that temperature into kinetic energy, which is done through the nozzle design. You can basically only turn that certain amount of temperature into a certain amount of kinetic energy because you only have a certain amount of energy to work with. And so it's really hard to actually change the exhaust velocity given a certain fuel. Basically, what this means is that the exhaust velocity is often fixed. So we choose a certain type of fuel that we want to use, and we get a very specific exhaust velocity. And then we have to set the mass flow rate to get the thrust that we want. So to get off the ground, we need a lot of mass flow rate because rockets are very heavy. To move around in space, though, we don't need very much mass flow rate, especially if we have a lot of time. And so what we often do is we often use really, really, really powerful engines with huge mass flow rates to get off the ground. But then we use smaller engines to move around in space because we've got a lot more time. And so we can use something that doesn't necessarily have as much mass flow rate. So the total mass of the fuel that we need to get off the ground, we can determine. We can use the rocket equation to basically figure out the mass of the rocket that we need, given the delta V that we desire and the exhaust velocity that we have. Remember that this rocket equation here, if you look through it, you don't find the mass flow rate anywhere. It's completely independent of the mass flow rate, but it is very dependent on the exhaust velocity. It's also independent of time. This equation doesn't tell you how long it's going to take to get your delta V that you want. It just basically says if you're exhausting some certain amount of mass, however long that takes, however quickly you do it, you get this delta V from that. So that's really interesting. To summarize, the thrust of the rocket is given by the mass flow rate times the exhaust velocity. The mass flow rate can be really easily changed by adding more engines. The total delta V is completely independent of the mass flow rate though, but it is totally dependent on the fuel that we have, the total fuel, and the exhaust velocity. The exhaust velocity is super hard to change because it's really driven by chemistry. So increasing the exhaust velocity, which we really want to do because it decreases the amount of fuel we need, it's really hard to change, but that's the thing that we really want to change. And we need new technology to actually change that exhaust velocity. And that's where the science in rocket science actually comes in, because the science of rocket science is a lot about increasing the exhaust velocity, changing that chemistry limited exhaust velocity to do something new, to basically make it so we don't need as much fuel to do things. And a lot of the lessons that are coming up have to do with new technologies for increasing the exhaust velocity and talking about this rocket science.